All right, we're going to quickly go through the solution to number 67 in section 9.3. Because we won't have time to do it in class. I want you to see the solution. So the solution has to do with Euler's constant. I want to make my line look a little better here. So we're given this series, this partial sum. So we have S of n equals the sum n equals 1 to n of 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over n. Now we know that an infinite harmonic series diverges, but we're dealing here with a partial sum of a harmonic series, and we're relating it to the natural log function. So the key to this problem is looking at an integral and relating that to the area of inscribed and circumscribed rectangles. So the part A asks us to show that the natural log of n plus 1 is less than or equal to S of n, less than or equal to 1 plus the natural log of n. I'm going to draw a picture. Here are my coordinate axes, and I'm going to sketch in the graph of 1 over x. And we're looking at x equals 1, 2, 3, and I'm going to go out here and go to n and n plus 1. I'm going to sketch in my rectangles. So we're going to inscribe and circumscribe some rectangles. Do this part in blue, right here, and here's my circumscribed rectangles, and I'm going to put one more point in here, n minus 1. And I'll put my inscribed rectangles in red. We're going to look at the inscribed rectangles as well. All right. This tells us that S of n is just f of 1 plus f of 2 plus f of 3 plus dot 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 to f of n. If we say our function is 1 over x. S of n is these things. Well, the area of the inscribed rectangles, going from 1 to n, the area of the inscribed rectangles, I'm going to call that a sub I, is f of 2. This delta x is just 1, so it's just the area is f of 2 plus f of 3 plus dot 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 to f sub n. That would be the area of my inscribed rectangles. Well, this is S of n minus this first term. F of 1 is just 1. So the area of the inscribed rectangles is S sub n minus 1. Now let's look at the circumscribed rectangles. I'm going to call that a sub c. The area of the circumscribed rectangles is f of 1 plus f of 2 plus dot 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 plus f of n. Well, this equals S sub n. Now we're going to relate these to the integral of 1 over x dx from 1 to n. The area of the inscribed rectangles is less than or equal to that integral. So S sub n minus 1 S of n minus 1 is less than or equal to the integral from 1 to n of 1 over x dx. Well, when I evaluate this integral is the natural log of x, and we're evaluating it between 1 and n. Natural log of 1 is 0. So S of n minus 1 is less than or equal to the natural log of n. And I'm going to add 1 to both sides, so S of n is less than or equal to natural log of n plus 1. Well, there's the first part of my inequality. Now we're going to look at the circumscribed rectangles. The area of the circumscribed rectangles is larger than this integral from 1 to n plus 1, because the last circumscribed rectangle goes out here to the right. So S sub n is greater than or equal to the integral from 1 to n plus 1, because my last circumscribed rectangle is out here, of 1 over x dx. So this gives us that S of n is greater than or equal to the natural log of n plus 1. Put those two together, and we have that the natural log of n plus 1 is less than or equal to S of n, less than or equal to the natural log of n plus 1. And that's what we were trying to establish for part A. Well, part B talks about this sequence. I'm going to switch pages here. Part B talks about this sequence, A sub n, which is the sequence of S of n minus the natural log of n. And we want to show that this is bounded. So we need to show that there's a lower bound and an upper bound. Well, I'm going to go back to this inequality that we came up with, and I'm just going to manipulate it. We're looking for the terms of our sequence are S of n minus the natural log of n. So I'm going to subtract the natural log of n from each portion of this inequality. And when I do that, I get that the natural log of n plus 1 minus the natural log of n is less than or equal to S of n minus the natural log of n. And that's less than or equal to 1. Well, the natural log function is an increasing function, so the natural log of n plus 1 minus the natural log of n is greater than or equal to 0. Well, if this quantity is greater than this, then we're guaranteed that it's greater than or equal to 0. So I can rewrite this as 0 is greater than or equal to S of n minus the natural log of n, less than or equal to 1. So we've bounded the terms of my sequence between 0 and 1. So we've shown that this is bounded. For part C, we want to show that our sequence is decreasing. To show that a sequence is decreasing, we need to show that A sub n plus 1 is less than or equal to A sub n for n greater than or equal to 1. So each successive term is smaller. Well, for this to be the case, we need that A sub n plus 1 minus A sub n is less than or equal to 0. So we're going to demonstrate that this is in fact the case. So I'm just going to write, based on this definition, A sub n and A sub n plus 1 and A sub n. So I get that S sub n plus 1 minus the natural log of n plus 1. That's A sub n plus 1 and n plus 1. And I'm going to subtract A sub n. S sub n minus the natural log of n. And now we're going to rearrange this. I'm going to write this as S of n plus 1 minus S of n, and then I'm going to put these two terms together and I get the natural log of n, so minus the quantity, natural log of n plus 1 minus natural log of n. I'm just rearranging and combining these terms. Well, let's look at the second quantity first. The natural log of n plus 1 minus the natural log of n. Well, that is just the integral from n to n plus 1 of 1 over x dx. And this quantity, we said that S of n, I'm going to go over here, S of n equals f of 1 plus f of 2 plus dot 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 f of n. So S of n plus 1 is just this with an additional term. So S of n plus 1 minus S sub n, all I'm left with, everything cancels out except this f of n plus 1. F of n plus 1 is 1 over n plus 1. So this quantity becomes 1 over n plus 1. Well, in terms of our graph, let me sketch out our graph here. Just a tiny piece of it. So we're way out here. I'm not going to sketch my axis. This is my x-axis. Here's my graph. I'm looking at an expanded view here. Here's n. And here's n plus 1. One over n plus 1 is the height of this little rectangle, and the width is 1. So this area is 1 over n plus 1. The integral from n to n plus 1 of 1 over x dx is the area under the curve from n to n minus 1. So 1 over n plus 1 is a smaller quantity than the integral from n to n plus 1 of 1 over x dx. So I have a smaller quantity minus a larger quantity. This has to be less than or equal to 0. So we've demonstrated, based on our definition of the terms of this sequence, that the sequence is decreasing. We've shown that it's bounded. We've shown that it's decreasing, so we have a bounded monotonic sequence. So the sequence has to converge to a limit. They call the limit in the book, they call the limit Euler's constant. And then for part D, what they're asking you to do then is approximate a sub 100 by calculating s sub 100 minus the natural log of 100. So s sub 100 is going to be 1 plus 1 half plus 1/3, dot, 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 up to 1 over 100. And then we're subtracting from that the natural log of 100. And that would be an approximation of this Euler's constant that we proved is the limit of this sequence. And there we go.